Picking up from my previous video where I discussed on-axis frequency response, in this video I'm going to focus solely on the off-axis frequency response and what that means in relation to on-axis. To give you another example again, on-axis would be speaker firing directly at you. Keep in mind that you are going to have a reference axis, a reference point, and in most speakers it is the tweeter, but some speakers, say for instance, a speaker with a large waveguide or something like that, usually the reference plane would be between the waveguide and the mid-woofer below it. But always check the manufacturer's recommendation for that, and if there aren't any, make sure to ask them because there should be a design axis that should be the reference plane. So going the next step, if you are looking directly at the speaker and that is on axis like this, then turning the speaker to the side, up or down, at any angle other than on axis would be off axis. And why does that matter? Well, as we discussed in the previous video, on axis sound is the direct sound, and it's predominantly the sound that's going to arrive at your ears first. If you're in a really small room, then you're going to catch a lot of off-axis sounds that are hitting the walls. If you're in a large room, you may not catch as much of the off-axis sound. And then there are other aspects too, like how close you are to the speaker. For example, if you're sitting very close to the speaker within maybe a couple feet, then you're going to be predominantly hearing the on-axis sound because the off-axis sound is going to be so much lower in level if it's a medium-sized room or larger. If you're sitting, a few meters away from the speaker and you're in a smaller room, then you're going to catch a lot of the off-axis sound, the reflections from the side walls, the ceiling, the floor. So it's not just that there is on-axis and off-axis sound, it's how those play into the room for your particular case. I mean, sitting close, sitting far away, large room, small room, these are all factors that you really do have to consider when you're not just considering purchasing a speaker, but looking at my data as well. And in my data, everything is referenced to 2 meters. The SPL is referenced to 1 meter, but the distance of the measurements are taken at 2 meters, and that is per the specification, the CTA 2034 that we discussed previously. When we talk about off-axis sounds, we talk about the off-axis sound in terms of horizontal and vertical. So you can probably imagine that on-axis and then off-axis, that will be horizontal because you're spinning it around on the horizontal plane. But if you tilt the speaker, move it up, sit below or above it, then that would be the vertical off-axis plane. The difference between those two is important to understand because a lot of speakers will behave pretty well, in the horizontal plane. And that means that their sidewall reflections are going to be close in sound signature to what you hear directly. I say a lot, and that's not every speaker, certainly, but in my experience so far, that's pretty true. But the real deviation comes when you're talking about the vertical plane. And that's simply because if you can picture a point source, for example, me, I'm a point source. I've got one vocal, one mouth that I'm talking out of, and everything is coming from here, low frequency to high frequency. But if you were trying to split my voice up over a mid-woofer and a tweeter, if they can't occupy the same space, then they're not a point source per se. They are, located, one's above, one's below. And that distinction means that you typically will have some kind of discorrelation between those two drive units. And when the sound is projected out into the far field or into your room, then you can pick up on those sounds if the crossover is not built well. And what do I mean by if the crossover is not built well? Well, the ideal speaker, at least in my opinion, would be one that acts as a point source. And you can get that through coaxial and concentric drivers, but they have their own issues. And those kind of things I will discuss in those reviews. For example, the KEF R3 I reviewed recently, I'll put up here. And then the Kali IN5 I'll also put up here or either in the description below. So there's always trade-offs with speaker designs. You can use a point source like a coaxial, or you can use a standard 2-way or a 3-way speaker design where you split up the frequency response through multiple drive units like a tweeter and a mid-woofer for a 2-way design. In my experience, the horizontal or the lateral reflections off the side walls are more important than vertical reflections. But with my data, I'm allowing you to see all of that. You can figure out what's going on above and below the primary reference angle line. And you can also find out what's going on to the side of the speaker. So for example, let's say that you've got a living room and for whatever reason, you're not able to point the speakers directly at you. And that would mean that you're typically going to be listening off axis or with the speakers turned off axis, facing straight ahead out to the room. And in that case, you may want a speaker that has a better off axis linearity than on axis linearity. And by that, I mean, if you have to angle the speakers maybe 20 degrees off axis from you, then you may want to go and look at the horizontal data and you may want to find a speaker that has a more flat 20-degree off axis response than a flat 0-degree on axis response. Now, certainly there is some wiggle room here, and this is kind of where you get into the region of preference versus reference. And I'm not necessarily here to tell you what's wrong or right, although it is said that most people prefer a flat on-axis response. But getting into the ability to have to turn a speaker one way or another to accommodate your room, that's where things start to get a little bit shaky. And that's where understanding the performance of the on versus the off axis response really helps you out. Therefore, in this video, I'm going to provide you with an example of some off axis data, and we'll talk about how I present that in different ways. This video may run a little bit longer than I would like it to, but there is a lot of ground to cover because off axis information is very dense. It's certainly a more dense topic than on axis response, but it is a building block to get you to understand what we're going to eventually, which will be the spinorama data. So let's go ahead and dive in and start looking at some off-axis data. The first bit of information we're going to discuss is the horizontal off-axis data. So in this case, I've got another example of the Kali IN5, same thing that I used in the previous discussion for the on-axis measurements. And here what I've done is I provided the off-axis measurements out to about 90 degrees. And one thing to keep in mind here is when you're talking about a speaker that is symmetrical, such as this speaker, where you could basically just, cut it in half right down the middle and it's the same both ways, that's a symmetrical design. And you expect that, it doesn't matter which side of the speaker you go to, it's going to behave the same way, either left or right horizontally. So what I do in those cases is I only provide you with 90 degrees out to one side because the assumption is that 90 degrees to the other side is going to be the exact same thing. There are some cases where a speaker will be a little bit different. Say, for example, the tweeter might be offset to one side or the other. And in those cases, you would have to actually measure and provide data for both plus and minus 90 degrees, because if you don't, there will be a discontinuity between the two. They won't be the exact same on either side. And you need to understand what side is the best for you to set the speaker up in order to listen to it and get the most fidelity, I suppose, that you possibly can. But in this case, this is a symmetrical speaker and I've only provided out to 90 degrees. Now, another thing is when you talk about horizontally, there really is 360 degrees. There's, 90 degrees to the side and then 180 to the back, and then the other thing going around the other side. I could provide out to plus or minus 180, but I don't because it just gets so messy in this graphic. And generally what I'd like to take away from this graphic is just to look at what's the trend as you move to the side. I mean, nobody's going to listen to the speaker behind it. Most people aren't even going to listen to the speaker beyond, maybe 10, 20, 30 degrees off axis. But I still like to see what's going on past that out to about 90 degrees, just so you can make sure that things are, well maintained. The response off axis is close in part to the response on axis. Let's look at the on axis again, just to recap. That is this maroon color. And, it looks pretty linear. It's not perfect, but it does look pretty linear. So now we're going to step to the side, 10 degrees. We're going to move just a little bit to the side and see what it looks like in red. And it's really hard to tell, but there is some deviation of the red, notably in this region, which is around 5 or 6 kilohertz. And then as you go a little bit higher, you can see a little bit of a deviation, but it's really not that bad. 20 degrees in orange, again, kind of the same thing, but you get more of a deviation here as you go off axis. And then for a strong example, let's look at this pink, this 90 degrees. Now what you see is you expect to have some kind of fall off rate because for the Kali IN5, the tweeter is in the front. There is no tweeter behind it. There is no tweeter to the side. So you expect that as you step around from the front to the side and to the back, that you're going to lose high frequency response. You're not going to be hearing the tweeter play anymore. And that's what you're getting here. But ideally, you would see a more smooth response here where there isn't a pickup of the high frequency and then a droop down again. Ideally, it would be more just kind of linear in this regression. It's not, but this really isn't bad. I don't really have a bad example to give you in this case. I mean, I do, but it's an older test and it's not really the same format, so I don't want to confuse you. But let's say, for example, a bad speaker might do something like this. It droops and kind of goes all over the place as you move to the side. That would not be ideal. And the reason for that is you really want the off axis response to mimic, in a way, the on axis response. The reason for that is if you take a sound that you have coming directly at you, and then you feed another sound to your ears, and that sound coming to your ears is vastly different from what you're hearing directly at you, there's going to be some confusion there. There's going to be some loss in fidelity. The tonality won't be right. Staging will be weird. And it's just, let's just say it's not a good thing, for lack of a better word. Those sounds that are arriving at your ear later, those are the reflections from the sidewall, and those are coming from the off-axis response. Therefore, you want the off-axis response to mimic, again, the on-axis response, so it helps add to it and doesn't really take away from the on-axis sound. I just mentioned a case where you might have a tweeter that was offset from the rest of the speaker and it wouldn't be symmetrical. This is such a case. This is the Focal Twin 6 BE, and I'll drop a picture here just so you can see what it looks like. And you can see that it has a tweeter offset from the mid bass and the mid range. And in doing so, I had to provide you with the plus and minus 90-degree response so you could see kind of what's going on here. And if you look at this, if you're not familiar with this kind of data, probably the first thing you're thinking is, what the heck is going on? But as somebody who is experienced at looking at this kind of data, I can assure you I thought the exact same thing. The reason for that is this is what they call a 2.5-way design. And it's kind of like a modified 3-way design where you have a mid bass playing a certain frequency range and you have a mid range playing a certain frequency range, but the mid range and the mid bass overlap a little bit to give extra bass output. And then you have the tweeter coming in at a higher frequency. And when you see these dips through here and you see all these other dips going on, well, that's a bunch of garbage, for a lack of better word. If you were listening to the speaker anything other than the near field, then you're going to catch a lot of those reflections. So in order to mitigate that, you would have to be close to the speaker. Now, luckily, this speaker is a near field design. It is designed to be a studio monitor. Just because you're sitting near field doesn't mean that the off-axis response doesn't matter at all. It still certainly does, but its effect is lessened because you're hearing much more of the on-axis response much, much earlier than you are with the off-axis response. So the off-axis response still colors the sound, but it's not as significant as it would be if you weren't listening in the near field. Now let's talk about the vertical response. This is the response that you get as you move from the reference plane above or even below the reference plane. And this data is informational because in some cases, you may not be able to set the reference plane directly up to your ear level. For example, you buy a floor standing speaker and your seats may be a little bit lower or higher than the tweeter is on the floor standing speaker. So you're off axis vertically a little bit. This information is useful to tell you where that's a problem. With this particular design, this is a point source design. It is a coaxial design, which means the tweeter is embedded into the mid-range area, so you get a more uniform distribution as you go above and below the speaker. But let's look at a case when you're talking about a standard 2-way with a tweeter and a mid-woofer. This is Klipsch's The Fives, and this is a 2-way design with a horn-loaded tweeter and a 4.5-inch mid-woofer. And what we can see in this data is, if we look, the maroon is the on-axis, and the on-axis isn't really that bad. It does have a upper frequency shelving going on to where it's boosted in the higher frequencies. But ignoring that, let's look and see how the vertical response mimics the on-axis response. So first we're going to start with the red. And notice in this case, I have a solid line and I have a dashed line. The dashed line is always going to represent the negative angles. And the negative angles is always going to be below the reference plane. In this case, the reference plane is the tweeter. Looking at just the solid red line, we can see that there is a difference in the solid red line versus the dark maroon line at the crossover region, which is around the 1 kilohertz to 3 kilohertz area, focused mainly on the 2 kilohertz area. But then outside of that, they line up pretty well. However, Going below the tweeter about 10 degrees, the dashed red line is closer in response to the on axis. Now let's look at the extremes here. Let's look at the green, 40 degrees below, 40 degrees above. And yes, I know nobody's going to sit that high, but I provide this data as informational so you can get an idea of what happens as you go to the extremes. Now we're looking at the dashed and the solid green lines down here, and we can see that there is a significant droop in the response, which means at the crossover region, the tweeter is not mated well to the midwoofer vertically. And unfortunately, it really doesn't matter if you go, above or below, you pretty much get the same response. And ultimately, what this data is telling me is that if I was going to listen to the speaker, I really will want to be either on axis or about negative 10 degrees below the reference plane in order to get the most linear response, because without that, you've got a droop in this crossover region. That's pretty much it in a nutshell for the off-axis response. However, there are multiple ways of looking at this data, and I provide so many, it might even be too many. And at this point, we're going to diverge into the other ways of looking at this data. Now, again, I want you to keep in mind that what we're about to look at is the same thing you've already seen. It's just presented differently. And the first way we're going to go about it is what most people consider kind of the standard. And then we're going to follow up with a special way that I've come up with to look at this data that I feel is more intuitive. For the next set of data, what we're going to start with is the Kali IN5's horizontal response. So we're going to switch over to the different method of viewing this same data. And here we are. This is a spectrogram, if you want to call it that, as I've known it called as other things like a contour graph. But regardless of what you call it, the data is the same. It's just laid out differently. So let me kind of walk you through and explain to you what the axes represent. Along the x-axis down here, again, you have frequency. And on the left side, what you have is something different. This is the angle of response. So starting with this dark black line here, or this bolded black line here, that is the 0 degrees line. And that is the same thing as what you saw here with this dark red line. Going back. Now, each of these angles is how far to the left or the right of the speaker you go, and you can go all the way behind, which would wind up being 180 degrees. So for example, if we were going to go to the right, that would be the positive direction. So plus 10 degrees is down here, plus 20, working your way up to plus 90, and then going up even further to plus 180 degrees. So all the way directly behind the speaker. Now, why do you need to know that? Well, it's kind of the same thing. It gives you an idea of what the speaker is doing in all axes. But remember how when I showed you this, I said I'm not providing you with 180 degrees worth of data because it would just be way too much to understand and to kind of sort through? That's why we have this graphic. The colors are set up to where you have 3 dB per bar. And what I mean by that is if you look over here on the right axis, you can see that the dark red is 3 dB, so it's 87 to 90 dBs. And then going down in color is 87 to 84, and then 84 to 81, so on, so on. And I wind up with blue from 63 to 60. And you may be wondering why I don't show all individual steps. In other words, why am I not showing, 90, 89, 88, and then 87, so on, so on, like 1 dB increments? Well, because it's really just hard to read that too. I've done it before. A lot of the feedback that I got was people prefer to have it laid out like this. And frankly, it's just a little bit easier to understand because the takeaway from this graph should really be what's the radiation pattern of the speaker. Radiation pattern is just a fancy way of saying what's the off-axis response going all the way around the speaker. And again, this is the same thing that you saw in the other graphic, but to me, this is a not better way of looking at it, but another way that will allow you to gain insight quickly and see different things depending on what you're looking for. Generally speaking, I'm looking for the red areas in this graphic. And what that's telling me is how far does the sound travel off axis? What that means really is, let's start on the low end. So generally speaking, all speakers on the low frequency area are omnidirectional, which means that they emit sound all the way around the speaker, frontward, backward, up, down, left, right, A, B, select, start. It's just all over the place, right? And as you go higher in frequency, that response starts to tighten up, becomes more focused, and it becomes beamed right at you. And that's how we come up with the term beaming. And that's also just another way of saying that the directivity pattern is going from omnidirectional to narrow, or wide to narrow. There's a lot of different ways you can put this, so I'm trying to throw them all out there for you now so you can kind of understand and remember, hey, I kind of have an idea of what Erin says when he's talking about this or when he uses this term. Now, back to the red. You can see that the red encompasses pretty much all angles from, negative 180 to positive 180. So all the way from the back of the speaker to the front of the speaker, you've got red on the low frequency region below about 200 hertz. But above about 200 hertz, you can see that there starts to become a break, I guess, if you will, where the response is not omnidirectional. It is more directional, which means it's more focused toward the front. And if you just look, you can see at 90 degrees, that's where that kind of starts to happen. So you're going omnidirectional on the low end, and then right around here, you go boom, and you jump forward. So then the next step that we see seems to occur somewhere around the 600 hertz region, where you go from about 90 degrees down to about 50 degrees. And then from there, you stay pretty well within that 50-degree radiation pattern. You do decrease in the directivity, and it narrows up to about 30 degrees in the high frequencies. But if you kind of just draw a trend line, that's what you're looking at here. Certainly the question that you may have is, okay, so what is ideal? Well, unfortunately, there isn't a single answer to that. Some people prefer a speaker that is completely omnidirectional, which means, again, that it is firing sound from 20 hertz to 20 kilohertz all the way around it. And if this speaker were doing that, then this whole graphic would pretty much be red. Some people prefer a more narrow directivity pattern, which means that depending on where they want that transition to occur, you might have just a beam of red from about plus or minus 10 degrees. That would kind of be the extreme. And anywhere in between is really where preference comes into play, and also where manufacturers' ability to make controlled dispersion or controlled directivity speakers comes into play. And I will say that I have yet to see one that is perfectly, within the same bounds from 20 hertz to 20 kilohertz. What typically happens is you see an omnidirectional pattern in the low frequency, and then a tightening up and a beaming of the high frequency content. And that's what we're seeing here. Now we're going to flip over and look at the vertical version of this graphic. And I'm going back again to the Klipsch 5s speakers, because that showed a typical response dip in the crossover region as you go above and below the reference plane. So remember, this graphic shows out to plus or minus 40 degrees. Now I'm going to go to this, and this has plus or minus 180 degrees. So it shows the entire bandwidth of the speaker from in front of it, this black solid line, to behind the speaker out here at 180 and minus 180. You're generally looking for the same trends here, which is, hey, where's most of the sound? What is the SPL? And in doing so, we can kind of see that, again, low frequencies are omnidirectional. And as you go higher in frequency, you start to lose directionality. The beam starts to tighten up, and the importance of being on axis to the reference plane really starts to increase. For example, if you look at the crossover region between 1 to 3 kilohertz, just in this ballpark area, we can see that the red dips down. And what that means is the SPL is high directly on axis, but as you go off axis, so if you go below the tweeter line to 20 degrees, you're losing about 6 dB of SPL. And if you go above the tweeter line to above, the 20 degrees, then it's kind of the same deal. You're losing about 6 dB versus the on-axis response. But then once the tweeter really starts to take back over, the pattern widens again. And that really just makes sense from the perspective of the tweeter playing low frequency is omnidirectional, but as it plays higher frequency, it becomes more directional. All speakers do that, and that's just beaming, and that's actually very easy to calculate. You can simply take speed of sound, which is roughly 13,500 inches per second, divide that by the diameter of the speaker that you're using, and then I normally cut that by 2, and that puts you right at the point where beaming occurs. And in this case, where this speaker is using a 4.5 or 5-inch drive unit, the beaming point is somewhere in this 2 kilohertz region. So we can see that the directivity starts to narrow up more through here, and then the tweeter takes over. It is omnidirectional, and then the tweeter stays pretty wide out to about 14 kilohertz, where it narrows up suddenly. And I believe that sudden narrowing is just simply due to this speaker is using a horn. And in this case, I think the horn, the geometry of the horn is causing that sharp dip in response as you go above, the 14 kilohertz region. Along those same lines, with respect to the crossover region, we've got this red where it kind of notches out through here. Another way you can check to see if there's an issue with the crossover is simply look at these other colors going on. See how there's a lot more of this blue? Blue is about 30 dB down from the red. And that means that there's a whole bunch of SPL lost right in this region, right where the crossover is. So this is not an ideal crossover for this speaker. Ideally, you would have a more smooth trend line between the crossover region as you hand off from the mid-woofer to the tweeter. Now we're going to switch over to a different way that I provide this same data. Again, this is all the SPL data, and this is the horizontal off-axis response. I created this script in MATLAB. It takes all that SPL data from my Clipboard output and puts it into what I consider like a polar or a global plot. In doing so, it helps me at least to envision the radiation pattern of the speaker just more intuitively. In this graphic, this is again the horizontal polar. And if you pay attention to this legend up here, what we can see is the front of the speaker is at the 0 degree axis. The back of the speaker is at the plus minus 180 degree line. And then the left of the speaker is to the negative side, negative 90 degrees. And to the right of the speaker is positive 90 degrees. This is a bird's eye view, top-down view of the speaker. What we can take away from this, what I take away from this, is there's a lot of kind of shifting going on in this pattern. Ideally, this would be more smooth throughout. Also, you really would like the speaker to stay within the same angle of response, meaning that, if it starts at 50 degrees wide, you want it to stay 50 degrees wide. I've not seen that yet. I'm not sure that I'll ever see a speaker that does that perfectly. So we kind of just, take what we can get. And in this case, the direction pattern starts in the low frequencies till about 510 hertz, which is marked by this. It is about plus or minus 90 degrees wide. So 500 hertz and below is basically forward firing from the left and the right of the speaker, all going forward. But then when you get to this region right here, which is about 800 hertz, you can see that that narrows up, and 800 hertz is about 60 degrees wide. And then as we step out to this line, which is 2.0 kilohertz, that is closer to 40 degrees wide. So as you go higher in frequency, the radiation pattern is going from omnidirectional to more directional, beaming, higher directivity. Again, this is the same thing that I showed you in this graphic. I just think this is a better way to look at it. And like I said, much more intuitive to me. I feel like with this graphic, you can picture the speaker being right in the center and then picture its radiation pattern from low frequency to high frequency. And one thing I will note about this graphic is on the low frequency end, it only goes down to 200 hertz because if I try to make it go down to 20 hertz, there just wouldn't be enough room in this graphic to do that. So I'll stop it short at 200 hertz. Now we're going to go back and look at the clipped vertical response. So here we are. Once again, same data you've already seen, just a different way of looking at it. And remember I talked about that 2 kilohertz crossover region showing a dip in directivity? Well, now you can really see it. This is a side view of the speaker's vertical response. So this is like you taking the speaker, setting it up, and then looking at it directly from the side. 0 degrees is coming out the front, 180 is at the back of the speaker, plus 90 degrees is the top of the speaker, and negative 90 degrees is the bottom of the speaker. And in this case, we can see that, again, low frequencies, a little bit more omnidirectional. As you increase in frequency, the response really should just narrow up or stay roughly the same, but it's not even following a trend line. Right around here, you've got a jump out in the frequency SPL. And what frequency is that? That's about, goodness, I'm gonna come all the way back around here, 1.3 kilohertz. Well, it just so happens that there's a strong port resonance right around here. And what we're actually seeing is the port radiating even more, causing higher SPL through this region. Now going to the next step, that 2 kilohertz region, you've got this blue area, which means it's 30 dB down from the red line. And the directivity is just tightened up to this crossover region because they didn't do a really great job of crossing over the mid-woofer to the tweeter, at least in regards to the vertical plane. And then once you get into the tweeter region, you can see that it opens up really, really wide. Now, just subjectively, when you have a speaker that's kind of jumping around in its radiation pattern, and it may go wide, narrow, or very narrow, and then very wide again, what I've learned, at least through my auditioning is that that tends to mess with the soundstage elements. So in frequency response, you have key areas. Let's say 1 to 2 kilohertz. If it's got a bump in SPL in that region, it may come out at you. It may sound a little bit forward. The same thing can be said, again, at least in my opinion, for the directivity patterns of a speaker. Meaning that if it gets narrow at one frequency and then it gets wide at another frequency, let's say you've got an instrument that covers both of those frequencies. Let's say, for example, 1 kilohertz and then 2 kilohertz. It's very wide at 1 kilohertz and then it's very narrow at 2 kilohertz. Well, that's going to throw off the soundstage. So you may get an effect that, may sound wide at one frequency, very narrow at another frequency. And the placement, as far as imaging goes, it may sound like that instrument is at this spot and this spot instead of just being at one of those spots. And that really messes with the soundstage overall. As I go forward and do more testing and provide this data, what would be really interesting to me is if you guys are able to correlate some of this as well, because certainly I've noticed these kind of things and I pick up more on it when you have a radiation pattern that does stuff that's just kind of all over the place. That's going to be it for this off-axis video. And in the next video, we'll talk about the spinorama data and try to combine what you've learned from frequency response on and off axis into a good set of charts that you can use to predict how the speaker is going to behave in your room. I hope you learned something. And if you appreciated it, make sure you give me a thumbs up. If you have any questions, as always, please feel free to leave a question below, and I will do my best to answer those as soon as I can. Until the next time, we'll talk to y'all later. Peace.